We will consider the Doppler effect now when the detector is moving and not the source. Again, we'll begin with the source emitting bleeps of sound with velocity v sound. And again, we'll have the period of bleeps t, and the frequency with which they are emitted will be f equal to 1 over t. The wavelength of such a wave, lambda, will be the spacing between two adjacent bleeps, and it will be equal to the velocity of sound times t, the period, or velocity of sound over the frequency f. Let's consider now what happens when the detector is moving toward the source. We'll start at t equals 0 when the bleep number 1 has just arrived at the detector. Sometime later, at time t prime, the sound wave has traveled toward the detector, and the detector at the same time has moved toward the source, so that the bleep 2 now arrives at the detector. And it has traveled distance d1 equal to v sound t prime. In the meantime, the detector has traveled distance d2 equal to v detector times t prime. The sum of the two distances adds up to the spacing between two adjacent bleeps, lambda, or lambda must be equal to v sound times t prime plus v detector times t prime. We'll factor out t prime, and so we'll get v sound plus v detector times t prime. Now, since the detector has actually moved toward the incoming bleeps, the time it takes for it to meet them and for the bleeps to arrive at the detector is less than what it would have been if the detector were stationary. In other words, t prime is actually less than the period with which the source is emitting bleeps. Or we'll write t prime is less than t. And of course that means that the frequency with which they're arriving at the detector will be higher. The bleeps will be arriving at a higher frequency f prime at the detector. And so we'll have lambda is equal to v sound plus v detector times 1 over f prime. Of course, lambda times the frequency with which the bleeps are emitted at the source must be equal to the velocity of sound, and so we can write that lambda is equal to v sound over f, that original frequency with which the bleeps are emitted, and that must be equal to the sum of the velocity of sound and the detector times 1 over f prime. Here f prime is the velocity of the bleeps as they're detected by the detector. Moving the terms around, we get f prime equal to f times v sound plus v detector over v sound, or that f prime is equal to f times 1 plus v detector over v sound. We see that the formula actually gives us higher value for the frequency with which the bleeps arrive at the detector, which is exactly what we expected from our analysis of our diagram. Now let's see what happens when the detector actually moves away from the source. So we'll go back again to that time equals 0 and the original position of the detector where it just has met bleep 1. And then a little bit later at time t prime, the detector now meets bleep 2, but it has moved away from the source. In that time interval t prime, the bleep number 2 has traveled again distance d1 equal to the velocity of sound times t prime, and the detector has traveled distance d2 equal to v detector times t prime. Now in this case, the spacing between two adjacent bleeps, lambda, the wavelength of the wave, is actually equal to the difference between the two distances d1 and d2. Or we can write that it's v sound t prime minus v detector t prime. We'll factor out again t prime and we'll get for lambda that is equal to v sound minus v detector times t prime. We'll see now that t prime, the time it takes for the second bleep to arrive at the detector, is larger than the period with which the bleeps are emitted. And so that means that the frequency will be less, that the bleeps will be arriving at the detector less frequently. Again, we'll have lambda equal to v sound over f, the frequency with which the bleeps are emitted at the source, equal to the difference between the velocity of sound and the velocity of the detector times 1 over f prime, the frequency with which the bleeps are detected. That leads, of course, to f prime equal to F times V sound minus V detector over V sound, or in other words, the frequency with which the bleeps arrive at the detector is equal to the frequency with which they are emitted by the source times 1 minus V detector over V sound. Now let's combine the results for when the detector was moving toward the source and when it was moving away from the source. And then we'll combine those two results with the results from when the source was moving toward the detector and when the source is moving away from a detector. We can see that all the corrections to the frequency with which the bleeps are emitted are very similar in form, so it's typical to combine them into one actually formula that looks like that. The frequency with which the bleeps are detected will be equal to the frequency with which they emitted, and then multiplied by a factor. That will depend on whether the detector and or the source are moving toward or away.